Hello.
Hello, good afternoon. How are you? This is Santiago speaking. Could you hear
Hi.
me?
How are you? Yes, we hear you very well.
Okay, perfect. That's fine. Happy to hear that. I am completely ready.
So I think we can start now. We ask everyone is with us. Thank you for joining us today. If you kindly write where you are from, what you do, what's your business, and which country you are from, just to help us to get to know each other more. So, like I write Shireen Musallam, I'm a consultant. I'm from Egypt. So please write.
Okay, so I guess that we can start. It's okay for all the audience to start now. So
Yes, just audience to get to know them. So you
okay,
have
so I'm going to try to share my screen. So please confirm me if you see my screen, please.
yes, we do.
Okay, perfect. So I'm going to widen to full screen for all the audience. So first of all, good afternoon, ladies and gentlemen. So this is Santiago Ferrer, a PM at the City Engineering Group in Spain. So thank you so much for the given opportunity to Symbios to be with all of you and present the capabilities and power of digitalization, simulation, and virtual twins onto the industry of any kind, from civil engineering to manufacturing, and also applied for smart cities. So for me, it's a real pleasure to be here with all of you. We are going to follow this index, starting with a general vision and fields of use of the digitalization applied to industry, the model-based systems engineering concept, the performance of virtual twins, its benefits, some new technologies from and to industry, and when changing gears to smart cities, I will show you some examples. So now let's start. Our first thoughts regarding digitalization goes to industry and manufacturing in particular. It's a really good starting point, but not the only one, as we'll see in a few minutes. So think about, please, about a smart city example. Regarding product engineering, we can use the virtual worlds to, first, the concept design and specification. We can come up with our first ideas in a computer and see from the start the foreseen performance of the item, component, or assembly we are designing. Even we can know if we meet specifications according to customer requirements and legislation. Everything from your PC or laptop. Systems engineering, hardware and software, and structural design, what is called as MBSE in the English parlance. It's possible to complement our design with all the ancillaries attached to the system from the hard and software standpoint and simulate the coordination. It's like a virtual testing, and here is a complete simulator where all the related in an unrisky and causing and giving information from all the LIoT sets. Now, and according to some sources, is about to be born very vehicles, electricals for a complete city. A complete manufacturing site can be replicated virtually with all participating elements. The engineering of full vehicles, data transmission, and the general working condition of any machine and process we can come up. Design, verification, validation, and final deployments. Virtually speaking, we can test everything to its limits, and see the maximum capacities of systems, vehicles, factories, and even complete cities, I will see later. So, in one word, the simulation of all processes via digital twins as virtual replicas. So, the virtual reproduction of a complete system. Thinking about manufacturing engineering, the virtual approach can be applied to first the process engineering, manufacturing lines, and tooling simulation. So all kind of processes, lines, tools, and stations can be simulated to the slightest detail. It's very important to remark the simulators and digital twins can get information not only from the real world, but also they are able to generate its own virtual data replicating the reality. That's really important as I mean to train artificial intelligence. That's the core of a digital twin. The algorithms especially designed to learn by themselves, applying machine and deep learning, and able to adapt and change their logic according to the input they received. Of course, supply chains, management, quality, and inspections are included in the concept of Industry 5.0, not 4.0, but 5.0. Think about computer vision and its capacity to identify objects and especially faults and effects of any kind, especially important in key areas such as aviation and electronics. So a digital twin is able to foresee unpredicted circumstances and risky environments much before they happen. It's important also to remark here the approach to the predictive maintenance for vehicles and assets. So how would it to know not only the operational condition of assets of any kind online and in situ, but to know in advance its evolution and when a likely breakdown can occur. So all measures to avoid these fall downs and challenges can be applied in the early stage, saving a lot of money and improving the user experience and customer satisfaction. Now, regarding the systems engineering as MBSE, model-based system engineering. So one of the strongest points is digital twins and the simulation of all types of industrial processes and assets applied to industry. Among the inner solutions, we can highlight, as I've said, the real-time simulators. It's very, very important, the concept of real-time, applying a system architecture based on models, what we know as MBSE, being able to communicate between different systems in real time through IoT devices.
What is MBSE?
Yes, it stands for Model-Based Systems Engineering. So it's, and the translation into easy language is the digital twin applied to everything, to the reality. So MBSE, Model-Based Systems Engineering.
So this like when you have energy monitoring system, maintenance system, how you connect them together?
Yes, so the disciplines is very wide, it's very ample. So basically it's based in IoT devices, capturing and gathering all the information, then performing the digital twin, and finally deploying all the systems and all the results to an application to the main user, to the end user. So the connection is to everything. So we can connect everything and we can gather all the information from any kind of assets. And what's important, the inputs and output of signals between machines, between vehicles, to manage the traffic in a smart city, the connection for traffic lights, even different platforms, regarding cars, UAV, drones, aerials, antennas, and so on. So the question goes for a very long conversation, believe me. Okay, so I hope that I answered your main question. So, of course, please feel free to all the audience to help me if any question arises. So, thanks a lot for the interaction. Okay, so with your allowance, we can continue because it's very important, as I've said, the concept of real time and the concept of MBSE, being able the communication of the different systems in real time through IoT devices. So with this approach, it's perfectly possible to come up with training devices, developing system models, user applications with powerful graphic engines such as Unity or Unreal. So it's possible to integrate any solution that may already to be in the customer hands while combining simulated and real systems, the hardware and software in the loop approach. Test benches can also be considered to gather all the systems. Here we see an example on the right side of this page of an electric motor, a physical asset integrated to a virtual urban bus. A virtual, not a real, but a virtual urban bus. Aiming the combination of real assets with a virtual environment perfectly matched. Continuing with the technology deployed, we highlight the capacity to generate synthetic data, virtual or artificial data from simulations for artificial intelligence training. So we do cooperative simulations, integrating simulators from different platforms and different suppliers even. We are capable of carrying out mission and capabilities training, for example, in the military fields, as well as the civil one, simultaneously with the help of a platform to gather all inputs from different kinds of simulators. We are capable of making digital twins according to the LVC approach. That's a very, very important concept. I mean, live, virtual, and constructive, linking real entities, real assets, live, with simulated and virtual environments, the virtual worlds, and in a constructive approach to introduce new and changing environments at will. So finally, we do the final validation work with the final customer. So on the right side, as a summary from a bird's eye view, graphically speaking, an array of our total capabilities, from design, artificial intelligence, simulation, digital twins, validation, predictive maintenance, and even cybersecurity. As core competencies, we can highlight the development of software of any type. So we need this software application, including application for the end users, databases, user interfaces, and communication between systems. We need to model any system if we wanted to get a very good approach, applying deep and machine learning, virtual models and digital twins in real time. So not in an out of time, but in real time, acquiring telemetry data from machines and vehicles via IoT devices. Here is when it comes to play the capacity to not to prevent, but to predict exactly what's going to happen in the future, establishing the tendencies of behavior and seeding the fields of predictive maintenance. Additionally, of course, we can combine 3D tools from another company, so it's possible to get accurate replicas of testing grounds to replicate testing conditions and real life of assets and machines. And also, it's a good idea to combine the displaying of information using augmented reality, superimposing virtual information to the real world. And last, but not least, it's possible to link applications related to virtual reality, with goggles, to enhance training and coming up with an immersive experience, improving the user experience field. In terms of design, we are able to develop, for example, cabins, cockpits, and ground control stations with HMI, human machine interfaces for industry in general and vehicles in particular, with which we have already entered the area of hardware developments, helping the validation with end users. So this can be linked to remote operation and automatic driving. So we'll see later of machinery, vehicles of all kinds, acting the human being as supervisor in a smart city. So we'll see later a very fine example. We should be able to perform the design of systems and better to say systems of systems. We have to remind any system and subsystems in any asset is linked to another one, making up a whole assembly working as a one and only entity. So now comes into the middle the micro design of electronics, for example. So this contributes to the final stage of validation and verification, the V&V, and unison with the final customer. As transversal skills, and to conclude this chapter regarding systems engineering, the merging of communications, developments, digital twins, and so on, I would like to mention a small array of transversal skills that it's useful to develop. I mean, firstly, the capacity of integration. So it seems easy, but it's quite complicated as being one of our capital know-how. The ability to make a conjunction between different systems from different suppliers at different platforms. So this basically enables us to certificate any system in front of the final customer and to perform a relevant role when applying maintenance following a user manual. On the right side of the screen, we see at a glance core competencies we have to observe and take into account if we want to fully get a virtual ecosystem in our industry. We go from the initial conceptual design to cybersecurity, passing through simulation, digital twins, IoT, predictive maintenance, and final validation. If we are able to embrace all of this, either by ourselves or with the help of a partner, we're on the right path to draw the main advantages from virtualization. The virtual integration comes from the hands normally of visual engines able to generate and show 3D environments. And not only that, but also making it possible the three most important capabilities for a virtual twin simulation. So I mean, first, the hardware in the loop, introducing real assets into the virtual worlds. Software in the loop, introducing any solution into the main virtual twin. And finally, that's a very important concept, the human in the loop, introducing the human beings into the virtual world. So now we get the three factors completely interacting between each other. Be in mind that the two most important powers of artificial intelligence is the ability of capturing and interpreting images, what we call as computer vision, and the ability to help us to make the most adequate decisions. So artificial intelligence is not going to substitute us, but to help us in our everyday work. So in this page, as a matter of an example, I've chosen an industry making the virtual twin of its air conditioning unit systems, virtualizing, pipelines, compressors, fans, conductions, etc. And to finalize this chapter regarding the industry, I would like to mention some key technologies growing very fast under the shade of the fifth industrial revolution we are living now. In some papers, they insist in the fourth industrial revolutions, but I insist in the concept of the human-centric fifth revolution. I mean, as we see on this screen, additive 3D and 4D printing. So I'm going to explain very briefly the concept of 4D printing. Imagine the case, for example, that all kind of parts can be manufactured in situ from all kind of materials, smart metals included. Imagine that you can design components able to transform its abilities and features depending on the environment and conditions, changing its shapes, its conductivity. Imagine how the world materials and electronics can be changed drastically, coming up with new devices including breakthrough capabilities out now of our imagination. Imagine, for example, the case in the health area, making devices perfectly adapted to the patients and their bodies with no trace of reaction. Even a factory can self-suffice making its own spares, so it's now no need to wait till any specific component comes from the main supplier from the headquarters. So we can make it by ourselves with improved performances. So in my understanding, sounds very, very good. And the other area I would like to mention is the one related to robotics and IoT, specifically the case of AGVs and AMR robots, vehicles and machines connected together via IoT in perfect harmony with humans. So on the right side of this page, we see an example of an AMR following a path not previously established on the floor. So now, with the digitalization, we can chase our goal dream of cities and factories perfectly automated and that's important, simulated via digital twins to ensure our growth. And now we are going to change gears and I would like to mention the importance of digitalization in such a specific area like a smart city, so our own environments. So with a digital twin and proper simulations, we can test and train the following. First, the traffic control, avoiding pointless traffic jams and hotspots. We can model the best routes and paths for transit and evacuation in case of emergency for all road users. We can take advantage of all sensors embedded in our own vehicles, of the like of radars, lidars, cameras, etc., to road inspection and see the status of signs, horizontal markings, and even the quality and degradation of the pavement. Here, a digital twin can not only detect but prevent the evolution of cracks, bumps, and ditches on the asphalt in order to prevent accidents, for instance. But also, we're able to have a complete up-to-date model of our environment in real time. So we are able to get accurate to the slightest details models of our streets and its real status. The second one, IoT communication from vehicle to vehicle, what's called V2V, and vehicle to everything, V2X. So it will be instrumental to share billions of bytes of information in the clouds and be knowledgeable about what's happening ahead of us and around the corner. Our vehicle can transmit and receive information in the same way to be updated about any danger, any incidency, any accident, or simply to choose the best routes to go from a point A to a point B. Using the virtual worlds, we can perform the self-calibration of ADAS sensors thanks to IoT and information from other vehicles. Now, it is not needed to stop a vehicle fleet for some hours in a workshop to recalibrate the sensors with specific tools. Now we can communicate with other vehicles and the infrastructure to get information and compare it with information we are getting by ourselves. So, as a summary, if there is a match, our ADAS calibration is okay. If not, we can take the surrounding assets information as a pattern and recalibrate our sensors online and in a matter of a minute. So online and in situ on the site. So this is especially important in elements and devices helping to cars running in cities and open roads. Imagine the case, for example, about the assistance for emergency braking and so on. Remote driving of vehicles in urban areas and open roads now is a reality made possible by IoT protection and the power of simulators and digital twins, replicating the environment, supporting an extra low latency. So we'll see later. So imagine how businesses can grow managing remotely and safety a fleet of vehicles in the fashion of taxis, vans, small trucks. So we'll see it in detail, I insist. And finally, real-time digital maps erected from data taken from vehicles and UAVs. Aerial platforms are possible to better plan the smart cities and factories of the future. So I insist in the fact of gathering information from the real world and combining it to virtual data generated by our own digital twins. So all in all, they contribute to better training of the virtual models. So as stated before at the beginning of this conversation, so I would like to continue giving you examples of how we can contribute in the city engineering group to the digitalization of a smart city. So we can start first with our first example, a real example. It's called the Road Digital Twin Project. So in this case, we use the vehicle's ADAS sensors as elements to capture data and information on public roads. So I mean cameras, GPS sets, and lidars essentially. So to do this, we make extensive use of artificial intelligence to detect the status of key assets of our roads, such as traffic signs, road markings, or cracks and potholes in the pavements. So we obtain data on the status and the GPS position. So these elements are processed to have an ordered data structure. We analyze it with big data and AI techniques and show the data to the end user on portable devices such as a PC, a tablet, or a handy. So this allows us to develop a predictive model of the evolution of the state of the elements of public roads. So we talk about a digital twin about the road, our street we live. So we can see on our screen that would be next on our street, on our city, and users as sensors the ones mounted in our own vehicle. So, for example, imagine the case as how many observers can we take into account running to and fro. Thousands of vehicles, thousands of cars can provide pristine information and become observers of what's happening in our environments. So these anonymous vehicles are a huge amount source of information susceptible to be built and analyzed to get a gigantic, a mammoth data set to train predictive models to better, in the short, mid, and long term, the condition of our own cities to the benefit of safety, especially, and efficiency. So, from my standpoint, is absolutely fantastic. Here we see the sensor structure that we have used on the top, on the roof of a conventional car. So we observed a radar, a GPS geopositioning module, a camera, and two LiDAR devices. And on the right side of this page, we see how the data is gathered with the front camera and is virtualized afterwards to get a model. So in this case, we see a horizontal marking on the pavements. And the two LiDAR devices with a coverage of 360 degrees gives plentiful information via an immense cloud of points. So vertically speaking, the field of view can reach between -20 and +70 degrees of coverage. Now the second project I would like to share with all of you is what's called the bus digital twin. And on this project, we deploy a network of IoT sensors to acquire the most relevant data from a fleet of urban buses. So, from basic vehicle parameters, such as the engine or occupancy level, to driver data and their workloads, making extensive use of artificial intelligence to extract true value from data. So it's very important to highlight, to remark, to note the importance of knowing the level of stress in professional drivers. As far as we know, a urban bus in the middle of a congested city can be a very harsh environment for everybody, for everyone. So our approach is to know in real time the level of tension withstood by personnel at the wheel, and specifically to train these people in the best management methods to be sure their performance at the wheel remains high and able to tackle to traffic congestion. So we talk about a cognitive training for people and the ability to predict when and how the drivers are going to be overstressed. With digital twins virtually replicating the bus, virtually I insist, we're able to generate synthetic data to improve AI algorithms and establish the predictive bias of real systems. We can follow analytical techniques or rely on data. So here we see the general scheme at the upper top of this page of the intercommunications between different systems. Based on available cartography, we're able to generate a 3D environment, and on it, we display the behavior model of the vehicle and also the behavior model of the pedestrians and the rest of the traffic and road users. Our system allows us to simulate different entities at the same time in a coordinated manner, generated synthetic data that can be combined with real data. So that's the power of a digital twin, the combination of virtual data with real ones. So complex algorithms for predictive maintenance and fleet optimization also can be deployed. So that is the vehicle sensors, as a summary, are integrated with the smart city ecosystem, and all the connected and simulated entities interact with each other. We have discussed along this conversation the importance of the IoT connection of sensors and their simulation and virtual environments. So within the framework of this vast digital twin project, our real-time simulator shows a very realistic graphical scenario with perfectly integrated human-machine interface devices so that multiple test grounds can be managed in a cooperative simulation frameworks. For example, just in the middle is reproduce the center of Madrid, for example. And another example is the case of Calix, the project to the self-calibration of sensors in vehicles automatically and in real time. So we acquire data from the vehicle's telemetry system, and we connect all this information through V2X, the communication between vehicles and infrastructure, and the protocol of 5G with another vehicles, and for example, with traffic lights, cameras on gantries, etc. So if we compare the data captured by our own vehicle and if it's coincident with the information transmitted by other vehicles and infrastructure, the probability, the likelihood that our sensors are well calibrated is very high. If not, we can self-calibrate our own sensors with information transmitted by third parties. Of course, reaching this point, we all agree that sensor accuracy is key, is very, very important. So nowadays, static calibration can take up to 2 hours of downtime. So with our technology, sensor calibration takes a maximum of 5 minutes. In addition, we can carry out continuous dynamic calibration. So this is a very, very important concept by comparison with other road users. In this particular case, we focus our attention to the ADAS system designed to assist us in an emergency braking. So now we can see the relationship and connection between other vehicles and infrastructures, transmitted information with our own vehicle safety suits. And this is a clear example, in my understanding, of collaboration between systems. So now smart systems talking between themselves and each other. So delving into the archives, and in this case of this sensor self-calibration project, I show you the architecture for the communication networks. Very simple at high level, linking through the communication gateways with both the intermediates and final nodes with artificial intelligence, real-time communication with databases, and data output to the user's HMI. So as this is truly an automotive, the main protocols are CAN bus and Ethernet of communication. And I would like to approach to a very important concept from my understanding, that it's the predictive maintenance. The predictive maintenance, not the preventive, but the predictive maintenance, allows us to anticipate maintenance operations and failures before they occur. In addition, we can design operations to improve any system. So in these cases, the city engineering group is in charge for analyzing all the information available from any source, analyzing the root cause if there is any failure, carrying out functional investigations, developing the model hypothesis, and identifying relevant variants and proposing variation methods. So that's the theory of the algorithm regarding predictive maintenance. So the case of Ecomobile 23, a Spanish project, is a good example of this. So now it's applied to an electric urban bus. So we can imagine the complexity of connection with the telemetry server, its data transfer to a database, predictive maintenance calculation modules, and the digital twin. So the digital twins are interacting and each other. So in this case, we've chosen what we judge as the key elements of an electrical vehicle. So now you know the electric motor, the battery packs, the ADAS system for emergency braking, the air conditioning units, and finally the wear and tear of brakes and tires. So we've done firstly a model of each subsystem. And once finished, the next step is to link every individual model in a one and only platform and play the interactions between systems. So in one word, it's to see what's happening when all the systems interact to each other. So we all agree that the status of the roads or the style of driving can affect strongly the life of the battery pack, the tires, etc. So this implication is linked to the economical operation of the vehicles and their efficiency, and with the help of our capacity to predict what will happen to the vehicle in the near future, we can, for example, to reschedule maintenance operations to best dates. We can reduce the stop times. We can optimize the availability of spares in a just-in-time approach, avoiding to accumulate tons of parts in thousands of cubic and square meters and saving a lot of dead money, as well as expanding the real life of the fleet of vehicles in consideration, decreasing to the minimum the stoppages due to breakdowns. So for me, this is a very good project as an example of systems of systems. Also at CT, we are participating in what's called the European Ecomobility Project, in which we are developing a traffic manager, so to speak, for an exemplified smart city. So as we've seen before, with the data captured from another vehicles, from a fleet of vehicles, with the help of their ADAS systems and the infrastructure, through V2V and V2X communications and with 5G protocols, we can make three-dimensional maps of the environments of our city, of our neighborhoods, of our streets. We developed predictive models to streamline the circulation of a large city and thus avoid incidents, traffic jams, accidents, make it transit between a point A of origin and a point B of destination more agile and faster, and significantly improving the user experience and contributing to a greater eco-sustainability. So we take advantage of vehicles sensors to capture data and images from our own environments to get an exact replica, virtually speaking, of what we are seeing. So the next step is to get a virtual and mapped environment, a map. So we can use for this tag graphic engines such as Unreal and Unity, said before, to simulate our smart city. And then we can put over there a fleet of vehicles. So it's important to remark, reaching this point, that our approach is to provide the vehicles with the capacity to decide by themselves how to go from a point A to a point B, depending on incidences and traffic. So the path trajectories are not predetermined in advance. So the point is to deploy smart models, smart cities, smart vehicles, able to decide inside to and online the best routes, the best, for example, mean speeds to avoid the red lights, the best parking lots. And all this is going to be achieved with extensive use, of course, the communications between land vehicles and, now let me say, aerial platforms. So what we call as UAVs or drones. So as we talked about the communications between assets and vehicles also, I would like to mention the need to secure these communications, especially in a smart city environment. So um, as you can understand, it's not the same the messages transmitted and received by commuters in their particular cars compared to the communications between military or patrol police vehicles. So we agree that strategic vehicles, such as from the police and the armed forces, needs a protocol of cybersecurity and encryption much stronger than what's needed for civil applications. So we are also implementing this added value layer of cyber protection, cyber armoring, and even backed up by blockchain to get a perfect traceability of the communication and links. So as a summary, and in my understanding, this is the perfect match for a smart city. You know, first, the 5G communications protocol, connectivity, V2B and V2X, artificial intelligence, predictive models based on machine learning and deep learning, cybersecurity, and blockchain. So I see that's the perfect approach. And with this application, with this initiative as an R&D, we even allow ourselves to advise you on the best driving strategy. So in this concept of city, of a smart city, we can deploy models for remote and autonomous driving. And also, I would like to share with you, as we talk about the remote driving, we are developing in recent times, so to speak, a remote driver station. So imagine the case that you are peacefully at your office or home and you are able to drive remotely a real car in the middle of a real city on a highway and in the middle of real cars and real city and road users, you know, bikers, pedestrians, skaters, cyclists, and so on. So now at City, we take care and we are in charge of the communication, firstly with the sensorized vehicle, you know, with the ADAS suits and the control actuators, the remote driving station, and the communication with the control center. And we are also developing a simulator impersonating the real vehicle, the real car. So as we talk about an automotive approach, the communication protocols we highlight are MQTT and UDP. So on the right side of the screen, we see the basic architecture, very basic at very high level for communications between different subsystems, that it's between the vehicle itself, the driving station, and the omniscient control center. So it's important to highlight the fact that it's resistant to general failures of communication networks, able to be working even with poor communications, and allowing ultra-low latency in information transmission, especially referring to video signals and commands to control the vehicle. So please take into account that, as a matter of an example, a latency in the region of 50 milliseconds at a speed of 70 or 75 miles an hour means the car can run without control for a time of between 4 or 5 seconds, and we're struggling to reduce the latency to the region of 10 to 15 milliseconds to minimize to the maximum extent the distance and time the vehicle could run uncontrolled. So the main advantage of this approach goes to fleets of taxis, vans, more trucks. So of course, one person cannot manage more than one vehicle at the same time, so it's obvious. But one person can be, how do you say, switch on or off from one vehicle to another without elapsed times in a matter of a few seconds. So, in one word, so this contributes to increase the efficiency of operation of vehicles and decrease, especially in transportation of goods, the legs with the truck fully empty. So, in one word, so remote control of vehicles is the threshold of autonomous driving and is perfectly married to the management of a smart city from the traffic standpoints. So we are going to make two type simulators linked to the vehicle. A basic one for the first integration of systems and a complete one showing the complete interconnection and a very realistic simulation. And finally, and to close this conversation, we are going to mention very quickly the main benefits of the simulator and virtual twins, that it's quality, safety, speed, reliability are among the most important benefits of sims and digital twins. So first, we can increase the quality in product and process design, as it's possible to correct initial errors from the outset. So this is really important, as we can launch a product to the market or commission a machine in a faster way. Human and machine can be introduced in the loop to assess all scenarios. So with this approach, we give the simulators all features to work in unison and not in a separate and an individual approach, less than useful way. So all assets simulator are safer, so we can detect from the outset any kind of failures in the design and the day-to-day working operation. So in one word summary, the prediction for a long life. And the last message, especially important for the financial areas, thousands of simulations can be performed without the needs of huge investments. So the advantage of simulators over the real essays based on errors and redesigns is more than evident. Okay, ladies and gentlemen, so that's all from my side. So thank you so much for your kind attention. And of course, if you have any questions, comments, so I will be more than happy to discuss openly. So thank you so much. Hello, is everybody there?
Yes, I'm here. I'm with you.
Okay, perfect. So thank you so much. So for a while, I was thinking about if there is any mismatch in the communication. So more than happy to send the witness that the communication is okay and the presentation has been recorded on time.
So do you like to take the questions?
Yes, please. I am open to discuss with all of you, with the audience. If anybody has any questions, I will be more happy to discuss and to answer. Yes.
Someone is asking, what is the difference between AI and machine learning?
So it's a very tricky question because the machine learning is specifically regarding how a machine can be automated and how can learn by itself. The artificial intelligence is a huge approach. It's like an envelope containing the machine learning and deep learning. And if you let me, I will also to explain regarding what's the deep learning. The deep learning is about to describe the tendency and the capacity of predict the future about what's going to happen next in the future with assets, with machinery, with vehicles, with the traffic as we've seen, etc. So artificial intelligence is an envelope, and inside are the machine learning, the capacity of the algorithmia, the software to learn by themselves, and the deep learning, the capacity to get the tendency and to predict, so to speak, the future.
Okay, another question. Someone is asking, is this when you were explaining the smart city? He was asking, is it useful? Is this useful for construction projects? And other meaning, useful to scan and detect the progress compared with the design and planned progress?
Yes, of course. The approach for a smart city, it's very wide and very ample. So now, of course, all the application, the software can be used for instructional purposes, to design the cartography of a city, to design the best routes for different points, to avoid hotspots, and specifically to streamline the traffic, the circulation in a city. So that's one point. The second one is to gather all the services to the citizens in one specific area. But of course, there are a lot of essays, and now artificial intelligence comes into play regarding the design of smart cities. Of course, the concept can be applied to any kind of cities. So any kind of cities are susceptible to be sensorized via IoT devices, and we're able to gather huge amount of information, tons of information, not only by the infrastructure itself, by drones, by cameras, but using and taking advantage about the road users, the citizens like you and me, and taking advantage about the sensors applied and embedded in our own vehicles. So all this, the connectivity between vehicles. Imagine the case, for example, that you receive in your own car that it's advisable to maintain and keeping a speed of about 25 miles an hour in an avenue to avoid all the traffic lights in red. So that's the communication, a smart approach between the infrastructure and the vehicle for instructional use and, of course, for the real assets.
Thank you. Thank you for the explanation. Someone is asking you another question, if you allow me. In construction, he say, his question, is it able to detect the new progress and also act as a quantity surveyor? Like in construction, you make surveys, what actual constructed versus the plan.
Yes, of course, there is a very important approach regarding the real assets, the constructed assets regarding streets, cars, building, traffic signs, horizontal markings, and the virtual ones. So that's very important, the approach to combine the real data with the virtual ones, because for example, imagine the case as we've seen the presentation. Imagine the case that we are going to predict the future on what would be the evolution of a crack or a bump or a pothole in a conventional street in the asphalt. Of course, it's not feasible to wait, for example, for a year about what could be the growing of this crack. So we are going to generate, virtually speaking, this model, these pictures, these images, this foreseeable evolution of this crack And with those virtual data, we're able to retrofit and to feed up the virtual twin to get much more quickly and much more cost effectively and much more efficiently. So what could be the evolution of these assets to prevent accidents and to repair this specific crack on the street, on the asphalt, much more quickly before any accident occur. Of course, with the use of virtual twins, and this virtual approach, we are able to predict how would be the evolution or the damage regarding the tear and wear on the asphalt, regarding traffic signs. Maybe a sign can be out of the verticality and it's needed to be changed or be erected to the verticality again. So with this approach, and it's very important to remark, in a portable device, the operator can get a whole picture not only about what's happening in their own city now at this moment, but the key is what's going to happen in the near future. So that's the connection between the real assets and the virtual ones. And the virtual worlds can be used to improve about what's constructed now.
So there is another question. He's asking, what is the difference between or the boundary limitation between image processing and computer vision?
Yes, and the computer vision is basically the analysis of images. For example, it's very useful in the case of maintenance. For example, that we are using drones, UAVs, to complement and to see about what's happening in an electrical grid, in a railway, in a dam, in a crane in a port. So, firstly, we deploy actually a drone to inspect these specific areas. So we take these images, but we need to develop artificial algorithms to know exactly what will be the evolution about what's happening in the near future with this with the status of this infrastructure. So now the computer vision analysis, to exactly to identify, for example, a crack, a defect, infrastructure, a metallic environment, even vegetation. So we need to train to educate this model with thousands and tons of information for similar pictures. So this discipline is what we call the computer vision. So it's a very wide specific area regarding the artificial intelligence. And now in the 21st century, we have made a lot of evolution progress regarding the identification of assets. So we are going much beyond not only the typical example on the internet about how it's possible to identify a person from a dog or from a cat. So now we are going much beyond in the sense, okay, so we are going to identify a specific failure, a specific breakdown in a vehicle, about the status of infrastructure, etc. So that's a very important approach. And now, I would like to say and to confirm you that at City, we are starting a very important initiative regarding the inspection of electrical grids in Spain and in Europe. So using drones and computer vision algorithm.
Thank you very much. It has been a very informative session. You have amazing knowledge.
A
That's
real pleasure
impressive.
for me. So I am very grateful to you, to Symbios, to the audience, and of course, I am at complete disposal if anybody can contact me via the email, via internet, via LinkedIn. I am completely open to discuss with anybody.
Sure. Thank you very much.
A real pleasure.
Have a great evening. Thank you. Thank you. Thank you, everyone. And this is a simple appreciation, certificate of appreciation from our team. We appreciate your time and effort and explanation. Thank you.
So you are very welcome, and I confess that I am more than happy to hold this meeting with all of you. And please count with me as soon as you can, as soon as you want. So I am complete, open to you, and at your disposal.
Thank you very much. Thank you. Thank you. We'll
Yeah,
learn it a lot from you too. And definitely we will be in contact. Thank you. Thank you.